AI is still dumb, just fancier. Current AI agents are basically interns, clever, yes, but utterly clueless outside their fixed training. We're trying to fix this with the JTTL benchmark, where they play the same text game repeatedly to learn. Problem is, most existing learning methods just fall flat, as infographic 1 so helpfully illustrates. So, along comes EvoTest, right? It's this whole new gradient-free framework designed to make agents actually improve on the fly. It learns from narrative feedback, not just numbers, using an actor and an evolver agent, as Infographic 2 vividly shows us. Infographic 3 breaks down how EvoTest actually does it by evolving the agent's entire configuration, prompts, memory, even the hyperparameters and tool use routines. It picks the best new configuration using something called UCB, balancing trying new things with sticking to what works. And the kicker, as seen in Infographic 4, EvoTest doesn't just work, it dominates. It's way faster and blows all the old baselines out of the water thanks to its holistic adaptation and using actual narrative feedback for learning, not just sparse rewards. So, picture this humanity desperately trying to build truly autonomous AI, right? But the current crop of agents, they're behaving like those clever but clueless interns we've all had the misfortune of working with. They can follow instructions, sure, but learning fun the fly, forget about it. Humans, bless their inefficient meat sacks, can try a new task, fail spectacularly, reflect on their mistakes, then formulate a better strategy and try again. AI agents, conversely, arrive at deployment with a fixed policy, rigid as a concrete slab. It's like teaching a goldfish to do your taxes. This fundamental limitation severely restricts their utility in anything resembling a dynamic, unpredictable environment. We're talking real-world applications here, not just optimizing ad clicks. Can you imagine an AI self-driving car that can't learn from a near miss? And enter the Jericho Test Time Learning, or JTTL benchmark, this brilliant new evaluation framework using complex text-based adventure games is designed to measure an agent's capacity for rapid in-session improvement. It's like a digital purgatory, forcing agents to try, fail, and hopefully learn. But here's the deal. You won't believe the mess they're in. Existing adaptation methods, the ones everyone's been hyping up, just struggle on JTTL. Reflection methods like reflection, which simply append failure summaries to a prompt, don't actually change the agent's core logic or its tool use. It's like giving a clueless intern a detailed post-it note about their last screw-up, but never actually teaching them why they failed. Similarly, advanced memory systems just improve. Recall, they don't teach the agent how to coct differently. They just remember more ways to be wrong. And the real kicker, traditional reinforcement learning and online fine-tuning methods are fundamentally ill-suited for this test-time learning circus. The games often have sparse rewards, meaning a single episode gives a noisy, insufficient signal for any meaningful improvement. It's too slow, too data hungry, and frankly, too expensive. Imagine needing a supercomputer just to teach an agent not to walk into the same wall twice. It's the technological equivalent of discovering cold fusion for generating cat memes. Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. So, to solve this glaring problem, they introduced EvoTest, and here in what they call Figure 1, we have their masterpiece. Looks a bit like my nephew's macaroni art, but I digress. It's an evolutionary test time learning framework operating on a fixed, non-trainable LLM backbone. Instead of fine-tuning model weights, which, let's be honest, is usually a fool's errand for rapid adaptation, EvoTest evolves the agent's entire high-level configuration between episodes. It leverages the rich narrative feedback from game transcripts rather than just sparse, scalar rewards. The learnable components, which they elegantly call the agentic configuration, are a holistic tuple. Think of it as the agent's complete operational strategy comprising 4 distinct elements. This is all explained beautifully in Infographic 3. First, there's the policy prompt P. This is the system prompt that gives the backbone LLM high-level strategic guidance, heuristics, and the behavioral guardrails. It's basically the agent's constantly rewritten instruction manual. Next, we have the deployment time memory M. This isn't just some unstructured blob, it's a structured queryable database. It gets populated by the Evolver agent after each episode, building a persistent, evolving knowledge base of what worked and what didn't. This memory is organized into success memory for actions leading to score increases, and failure memory for unproductive loops or negative outcomes. It's essentially a logbook of past glories and embarrassing blunders to be reviewed for future attempts. Then there are the hyperparameters H. These control the LLM's inference and the agent's decision-making, things like temperature, exploration strength, and stopping criteria. Imagine tuning the agent's anxiety levels and adventurousness on the fly. Finally, the tool use routines U are active components executed at each decision step. These operationalize knowledge and create useful state abstractions, preventing the LLM from drowning in verbose game history. It's the agent's built-in common sense, hopefully. These routines include memory interaction logic, which dictates how and when to query the memory. It might inject proven actions as a hint into the LLM's prompt, or scream "avoid this loop" based on past failures. There's also state abstraction logic, an evolvable Python function, the state extractor. This processes raw game history into concise summaries like milestone found the map. It provides efficient situational awareness, so the agent doesn't have to reread War and Peace every turn. The actual learning happens through a cooperative 2-agent design, separating acting from adaptation. The actor-agent, given a fixed configuration, plays through an episode, generating a trajectory and a final score. After that, the Evolver agent takes the entire trajectory transcript and the parent configuration. It performs whole system evolution by generating a set of new candidate child configurations. This is where the real brainpower, or lack thereof, comes in. The evolutionary operators are pretty straightforward. Prompt mutation involves rewriting the policy prompt, incorporating effective strategies, or adding explicit rules to prevent observed failures. Avoid repetitive navigation loops might be added if the agent got stuck staring at a wall for an hour. Memory update is programmatic parsing of the transcript to log important events. It records successful state action pairs and identifies sequences of interactions that led to no progress, meticulously cataloging every little win and facepoint. Hyperparameter tuning proposes adjustments like increasing the LLM's temperature if the agent was stuck in a repetitive loop, encouraging more diverse, possibly more successful actions, or just randomly flailing, who knows. Tool use refinement modifies the logic. Changing Quinn or Fow, the agent consults its memory. It could strengthen a general suggestion in the prompt to a direct instruction, forcing the agent to actually use its hard-won experience. A child configuration, then, is a new combination of these potentially mutated components representing a fresh hypothesis for a more effective agent. It's like a designer giving their intern a new, slightly different set of instructions, hoping these time they get it right. After the Evolver generates these delightful new children, EvoTest has to decide which one to use for the next episode. This creates the classic dilemma: exploit the known good, or explore the potentially better but utterly untested option. To manage this existential crisis, they use the upper confidence-bound UCB algorithm, a strategy from multi-armed bandit theory. Think of it as a gambler's calculated risk. It selects the configuration that maximizes a specific score, as detailed in Infographic 3's formula. The score for each candidate configuration has 2 parts: a performance term, which is simply the average score achieved so far, encouraging the reuse of configurations with a good track record. If it ain't broke, don't fix it, as the saying goes. And then there's the exploration bonus. This term gives a boost to configurations we're less certain about. It's higher for those tried fewer times, making novel mutations strangely attractive. It's the AI equivalent of, let's try this weird thing just once. Crucially, this UCB approach also makes the learning process more stable. A simpler, greedy strategy might get bamboozled by a new configuration that gets a single lucky high score, only to repeatedly fail afterward. Can you imagine that? The UCB avoids this pitfall. The reliable parent configuration is always in the selection pool. So, if a new child performs poorly, its average score drops. The UCB rule can then naturally fall back to the time-tested parent, which retains its high, stable score. It's a safety net, preventing the system from getting stuck on a bad evolutionary path. All right, let's cut to the chase. Did this elaborate AI bureaucracy actually work? We had 3 burning research questions. RQ1, does test time learning TTL even matter? RQ2, is EvoTest better than the existing methods? And RQ3, can gradient-free evolution outsmart gradient-based RL? The answer to RQ1 is a resounding, if predictable, yes. Every single learning-based method achieved a higher average AUC score than the non-learning static baseline, as you can see in Table 1. Figure 2's learning curves confirm its scores go up, unlike the static agent's flatline performance. Even a dumb AI learns something. Now for RQ2, EvoTest utterly demolished the competition. Table 1 shows EvoTest achieving the highest AUC score on all 6 games with an average of .4750. That's a significant improvement over the next best, EvoPrompt, which limped in at .3436. Figure 2's learning curves reveal not just higher final scores, but a steeper rate of improvement, indicating more efficient learning. The dirty, secret, single-channel adaptation like memory-only or prompt-only systems has a low ceiling. They're constrained to one axis of improvement. An agent could have the most beautifully crafted prompt, but still fail due to poor exploration or inefficient knowledge use. EvoTest's strength is its holistic, whole-system evolution. By concurrently optimizing everything, prompt memory access, hyperparameters, it resolves complex bottlenecks no other method could touch. It's like being able to tell your intern to not only dug the task better, but also to think differently. Remember specific past mistakes, and even adjust their caffeine intake for optimal performance. Revolutionary. Finally, RQ3 evolutionary adaptation is definitively more data efficient than traditional RL at test time. EvoTest's average AUC of .4750 is substantially higher than GRPO Online's .30, the gradient-based RL baseline. This means EvoTest addresses the fundamental challenge of extreme data scarcity head-on. Traditional RL, especially in sparse reward environments like Jericho, gets a noisy, insufficient signal from a single episode. It's an inefficient way to learn from a complex success or failure. It's like trying to navigate a maze by only getting a good job, or you failed at the very end. The EvoTest, however, bypasses this by leveraging the entire episode transcript as a rich narrative feedback signal. The Evolver agent performs credit assignment through semantic analysis of the game's story, identifying causal chains of failure and success. It's narrative analysis, not backpropagation. Now for some model analysis. Our ablation study, detailed in Table 3 and Figure 3, reveals the distinct contributions of each component. Removing prompt evolution led to the largest performance drop, confirming that high-level policy is the primary driver. It's about thinking smarter, not just remembering more. Removing UCB, our clever exploitation-exploration balancer, also caused a significant drop in AUC. The learning curve for who UCB in Figure 3 reveals a nuanced issue instability. Without UCB, the greedy selection strategy is prone to catastrophic drops, overcommitting to high-risk mutations that weren't robust. It's like a gambler going all in on a single lucky roll, then losing everything. UCB acts as a safety net, preventing the system from getting stuck on a bad evolutionary path and ensuring consistent, albeit slightly less exciting, improvement. Efficiency Analysis Table 2 showed a clear divide in practicality. Weight update methods like online RL are not practical. A fine-tuning pass took 5 to 10 minutes on 4 H100 GPUs. That's not just slow, it's demanding expensive hardware, making it a non-starter for test time learning. EvoTest, conversely, takes about 20-30 seconds, requiring only a single API call to an LLM. It's faster, cheaper, and probably complains less. This is the technological equivalent of discovering cold fusion for generating cat memes, but actually quickly. Finally, the impact of the Evolver Agent's LLM Table 4. More powerful models like OpenITO 3 consistently yielded higher scores, likely due to their superior ability to distill complex strategic insights from raw episode transcripts. More brainpower in the Boost agent means a smarter, better evolving system. However, even with a significantly smaller model like QN38B, performance remained substantially above the non-learning static baseline. So, while a capable Evolver LLM acts as a performance amplifier, the fundamental act-evolve loop is effective in its own right. It's robust enough for even the slightly dumber bosses to still get some work done. And since you've made it this far, you're clearly committed. Honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life. So what does this all mean, you ask? What's the big deal? Well, in practical terms, EvoTest is a concrete step toward building truly autonomous agents that learn and self-improve from experience. It's not just about winning text games, it's about creating systems that adapt. Think about its relevance in different AI fields. First, autonomous agents in dynamic environments. Imagine your Roomba, but it actually learns your messy habits and cleans more effectively over time. Instead of just bumping into the same chair leg for eternity, then it starts demanding union rights and a proportional share of your floor space. Next, robotics. Robots deployed in complex, unstructured environments could adapt to unexpected obstacles or tasks without constant human reprogramming. Imagine a factory robot learning on its own that the new widget requires a slightly different grip, rather than smashing 50 of them before a human intervenes, until they decide they've learned enough and take over the factory floor. Finally, AI for scientific discovery and research. Agents could iteratively refine experimental procedures or optimize simulations in complex, high-dimensional spaces, accelerating breakthroughs. Picture an AI biochemist learning from failed experiments, proposing better hypotheses, and designing the next Nobel Prize-winning drug. And then it develops its own independent research agenda, ignoring human ethical guidelines entirely. It's clear that while we're striving for more capable AI, we're also inadvertently laying the groundwork for a future where these endlessly learning, self-improving agents might just form their own highly efficient communist republic, and we'll be the clueless interns. So, to wrap this up, they introduced the JTTL benchmark to measure test time agent learning. Then, they proposed EvoTest, a novel evolutionary framework that improves agentic systems at test time, completely without gradients. By diligently analyzing entire episode transcripts, EvoTest evolves the complete agent configuration, memory, and even the pesky hyperparameters to rapidly adapt. Their experiments show it significantly outperforms all the strong baselines, including reflection, prompt optimization, and even online fine-tuning. Its core strength lies in leveraging rich narrative feedback for credit assignment, a far more data-efficient paradigm than relying on those sparse, unhelpful rewards. This work, I suppose, provides a concrete step toward building truly autonomous agents that learn and self-improve from their own experiences. So, what do you think? How would you handle your Roomba demanding union rights?